Okay, we'll get started here. I'm just going to do some catch up here. I want to finish up chapter 8, and chapter 9 is pretty short, so we'll cover that, and then jump to 10 for today's lab. And so chapter 8, we're talking about the energy level diagrams here, the difference between a single electron and a multi-electron species. In multi-electron species, we see that the 2s and the 2p are no longer energetically degenerate. If you look, there's a shift also here, because when we're going from a hydrogen atom to a lithium, lithium has 3 protons in the nucleus. Having 3 protons in the nucleus is going to pull the electrons closer in and lower the energy. And so this is why there's a drop here in terms of energy. We see a drop here and a drop here associated with these species too, as the energy and the size of the orbital is lowered or small. Anyway, what causes this splitting here? The 2s and the 2p are no longer degenerate. 3s, 3p, 3d, no longer degenerate. So what was the cause of that subshell splitting? Shielding and penetration, right. We say that the 2s are more penetrating than the 2p. The more penetrating ones are going to be lower in energy because they're less shielded. And the same thing, 3s, lower than 3p, lower than 3d. 3ds aren't very penetrating at all. And so the diagram that we want is neither of these. The diagram that we want to remember for multi-electron is this. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Here. This is the diagram we should focus on here because this is the first shell, right? In the first shell, how many subshells are there? 1. Right? Second shell, we have 2 subshells, right? Third shell, how many subshells do we have? We only have 2 subshells. And so, the other day I was saying, well, in the third shell or third level, we should have 3 sublevels or 3 subshells. So it gets a little bit more complicated when we have this splitting here because there are n sublevels for every n. And so when n equals 3, we do have 3 sublevels, but 2 of them are in the third shell, 1 of them is in the fourth shell. And so that's not that important because this is much higher in energy, this 3D. And so we should just focus on these here. And so this is the third shell. In the third shell we have these 2 subshells. In the fourth shell, in the fourth shell we should have 4 sublevels, but we only see 2 of the 4 sublevels. The other 2 are higher in energy, and then we have this 3, n equals 3. And so this is the fourth shell. And so this diagram is the diagram you want to be able to draw, for multi-electron. We're just going to draw it like this, where the 4s pops in here. And so we have the 4s popping in here and the 4p's there. Okay. And so we'll show it that way. All right, now we need to start filling these with electrons. Did I talk about the off-bow principle? No? Hund's rule? The Pauli exclusion principle? Where did we leave off last time? Right here? All right. So let's go ahead and draw. I'm going to draw the energy level diagram for a multi-electron species. The energy level diagram starts with the 1s orbital. The 1s orbital is also known as the what? NLM. The 1s orbital is also known as the 100 orbital, right? And then after the 1s orbital, we have the 2s orbital, which is a 200 orbital. And then slightly higher in energy than the 2s are the 2p orbitals. I'm going to draw them over here, because the L is equal to 0 over here, L is equal to 1 over here, so this is a p orbital. And so we're going to have 2, 1, negative 1, 2, 1, 0, and 2, 1, 1. And then we pop up a little higher. We hit the 3s, which is 300, and then the 3p's. The 3p's will have the 3, 1, negative 1, 3, 1, 1, and 3, 1, 3, 1, 0, and 3, 1, 1. Those are my 3p orbitals. That's in the third shell. And then I'll pop up into the fourth shell, which is the 4s, or the 400. After the 400, the next higher orbital subshell is the 3d. We have 5 of those. So what are they? They're the 3. Did I already do this? Okay, 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. And then to complete the fourth shell, we need the 4p subshell. The 4p are slightly higher in energy, so the 4s, the 3d to 4p. The 4p are going to consist of these 3 orbitals, which are going to be the 4, 1, negative 1, 4, 1, 0, 4, 1, 1. And so you should be able to draw this energy level diagram up to 4p and be able to label them.
The 3D is lower than 4P.
The 3D is lower than 4p. Yeah. But higher than 4s. Okay, so it's sandwiched between the 4s and the 4p.
Why do you do like 4, 1, minus 1 or 3, 1, minus 1 and not?
Why do I do that? Because those are the quantum numbers for each of these. This is N, L, M. And so each orbital has a unique set of quantum numbers. So for example, when we're looking at 3p, there's 3 3p orbitals. If I didn't have quantum numbers, what would you call each of them? Would you say, oh, that's the left one, this is the middle one, that's the right one? No, because they're all, really they're just orthogonal to each other. And so we have to have some kind of distinction. Which one lies along the x-axis? Which one lies along the y-axis? Which one lies along the z-axis? That distinction comes from the last quantum number. The -1, 0, and 1 tell us the orientation. And so these are the orientation, and since I have 3 different orientations, I have a total of 3 orbitals in this subshell. And so I do this because rather than saying I want an electron in the middle one, I just say I want an electron in the 310 orbital. And so each line has a unique address, basically. It has to, because these come from quantum, the Schrodinger equation. Now, when we fill electrons in, this is multi-electron, so we're going to fill electrons. When we have single electron, it's pretty easy. You just put it in the lowest energy, if we call it the ground state. The ground state is going to have the lowest energy, or we could put it in a higher energy, which would be an excited state. And so filling electrons for ground state electron configuration. So we're looking at ground state here. And we just have to follow a set of rules. The first one is the off-bow principle. Off-bow, all he says is this: fill the lowest energy ones first. Fill lowest energy first. Unless it's an excited state. If it's an excited state, then you can put an electron anywhere you want. But if it's a ground state, we want to start off with 1s and then build our way up. And so that's the off-bow. The other thing is, sometimes we have degenerate orbitals. What does it mean, a degenerate orbital? A degenerate orbital means they're the same energy. And so if we have a degenerate orbital, then which one do we fill? Well, it doesn't matter which one you fill. You fill any of these 3. And so, for example, here, hydrogen has 1 electron. Did I talk about the 4th quantum number? No, I got to talk about that in a minute. And so we have something called Hund's rule. Hund's rule, there's something called electron spin. Probably aware of that already. But Hund's rule says fill degenerate orbitals one at a time. Degenerate orbitals one at a time with parallel spin. Okay, I'll talk about spin in just a minute. And 3, we have the Pauli exclusion principle. Pauli exclusion principle. The Pauli exclusion principle just says that no two electrons in the same atom can have the same set of 4 quantum numbers. And so far I've just talked about 3 quantum numbers, N, L, M. These 3 quantum numbers come from the Schrodinger equation because they're related to psi. Each psi depends on N, L, and M. For the psi to solve the Schrodinger equation, there's certain restrictions on the N, L, M values. But it turns out there's a 4th quantum number, which is purely quantum mechanical, and that's electron spin. Electrons are going to behave like little magnets. And, you know, little magnets are going to have a north pole and a south pole. When something has 2 poles, we call it a dipole. And so it's going to have a magnetic dipole. The north pole could be pointed up, or the north pole could be pointed down, you know, that kind of thing. In other words, I don't know, but we call this the spin-up configuration, so we just show an arrow oriented like that. Or the electron can be spin down. Now, the 4th quantum number is associated with whether it's spin up or spin down. And the 4th quantum number comes from the math, and so this is why it's a fraction. The 4th quantum number says if it's spin up, we call it plus 1/2. If it's spin down, we call it minus 1/2. Yeah, this is for dipoles like this. You could have multiple poles, not just a dipole, and then you'll get, but not for electrons, for atoms. Anyway, it's either plus 1/2 or minus 1/2. And so the way we're going to represent electrons filling our energy level diagram is with arrows. And so if I have hydrogen, if I want the ground state of hydrogen, I put an electron in the lowest energy orbital. And I have a choice. I could place it spin up or spin down. Does it matter if it's spin up or spin down? You know, is there an energy difference between an upside down hydrogen and a right side up? Well, you know, what is upside down? What's right side up? Right? We know because gravity, you know, gravity interacts with masses, but you know, gravitational force is not significant for hydrogen, and so it doesn't matter. The only time it matters is if there's another electron or if the atom is in an external magnetic field, like in the Earth's magnetic field. If something's in the Earth's magnetic field, then it's going to make a difference if it's aligned with the field versus opposite the field. It's like 2 magnets. If you try to put south and south together, one of them tries to flip, or both of them try to flip to reorient north-south, south-north. But here it doesn't matter. I can put it spin up or spin down. Either is going to be the exact same energy. And so when I have this, the way we identify this electron is this electron's in the 1,0,0 orbital with the spin up. And so we assign 4 quantum numbers to this electron. The first 3 identify the orbital, N, L, M. The 4th define the spin. And so this is plus 1/2. And so this is N, L, M, S. Those are the 4 quantum numbers that define this. And so that would be hydrogen. Just out of habit, I put it spin up, but I could have put it spin down. Same thing. For helium, we have 2 electrons. And so what we can do is we can put one more electron in this orbital with spin down. If we put one more electron with spin down, we get 1,0,0, which defines the 1s orbital, minus 1/2. And so those are the 4 quantum numbers that define this electron. 3 of them position it in one of the orbitals, and the 4th one tells us what the spin is. Now, could I put a 3rd electron in this orbital? I can't put a 3rd electron in here because the 3rd electron would either have to be spin up or spin down. There are only 2 spin orientations that are allowed. And so if I put it spin up, then it has matching quantum numbers with this. If I put it spin down, it has matching quantum numbers with that, and it's a violation of the Pauli exclusion principle. The Pauli exclusion principle tells us that the maximum capacity of a single orbital is 2 electrons with opposing spin. And so if I have a third electron like lithium, I'm going to have to go to the next higher energy orbital, which would be a 2s. The 2s, I can put it spin down or spin up, doesn't matter. Out of habit, I'm going to put it spin up. And so this would be a 2, 0, 0 plus 1/2. Then I go to beryllium. Beryllium would be a 2, 0, 0 minus 1/2 on top of that. So beryllium is 4 electrons. And then I can continue going on. After beryllium comes boron. Now, which of these should I fill? Does this violate anything if I just pick the third, the 2, 1, 1 orbital? Is that a violation of anything? No. I can pick any of these orbitals I want because, you know, the only difference is they're just orthogonal to each other. So one's along the x, another's along the y, and another's along the z. It doesn't matter which one you pick. All going to be the same. But once I pick one, then Hund's rule says that the next electron has to go into one of these, and it doesn't matter which one because they're both 90 degrees apart. And so I could just pick this first one here. And so now I have carbon. You know, carbon has that many. And so when I go to nitrogen, I have another electron I got to put in there. And so all these have to be parallel spin. Otherwise, it's what we call an excited state. You know, it's not the most stable configuration. Once I go to nitrogen, I need to go to oxygen, so I got to pair one of these. Which one should I pair? It doesn't matter. People just pair the first one. This would be oxygen, and then fluorine, and then neon. And so what we see here is this. The first shell's filled, we end up with helium. We fill the second shell, we end up with neon. Helium and neon are noble gases. Noble gases are highly unreactive. And so there's got to be some stability in having a filled shell. You know, the symmetry of having a filled shell. And there is symmetry because when you fill up the entire shell and look at the electron cloud looks like a sphere. You know, this is what we call spherically symmetric. And so there's some symmetry and some stability to that. If we continue, we could fill up the third shell. You know, the third shell starts with what element? If you look at the periodic table, we can see what element the third shell. In fact, the periodic table is based on the shells. And so the first period is the first shell. The second period, from lithium to neon, is the second shell. The second shell consists of the 2s orbitals, which lithium and beryllium fill, and the 2p orbitals, which boron through neon fill. The third shell starts with sodium and ends with argon. And so when I get one electron in the 3s, that's sodium. And then from sodium, I go to magnesium here with 2. And then from magnesium, I go to aluminum, silicon, phosphorus, and then sulfur, chlorine, and finally argon. And so when I fill up this third shell, I'm at the argon configuration. So now I have 3 filled shells. All right, so what do you need to do? You need to be able to pick any electron here. So for example, if I pick this electron, what are the quantum numbers for this electron? This first one. 3, 1, minus 1, plus 1/2. No. And so that's going to pretty much pinpoint. So each electron has a unique set of quantum numbers. That unique set of quantum numbers, we can position it and figure out its spin. The other thing is you have to write an energy level diagram like this. Right? And then finally, we're going to do some comparison. And so we're going to continue with this energy level diagram, but I want to show you. In your homework, you probably aren't going to be writing energy level diagrams like this. because they take up a lot of space. And so in the homework, what Petrucci likes to do is he likes to write orbital box diagrams. And so if we're to look at argon, you know, he would have boxes like this: 1s, 2s, 2p, 3s, 3p. Yeah. And then we just fill it up for argon. You know, if we fill up the first two, this is, you know, helium. And then if we continue here, we get neon here. And then finally, filling up this third shell, we'll end up with argon out to here. And so there are different ways we can represent argon. You know, this electron configuration can be represented as just this, argon in brackets. That's what that is. Or if we want to show the outermost shell, what we could do is we could write neon, you know, like this, to represent everything up to the second shell here, and then write 3s2, 3p6. Well, 3s2, 3p6, that's a filled third shell. So we have all these shells. So the valence shell is filled. The valence shell, we have different electrons here. For example, these inner shell electrons are called the core electrons. Inner shell electrons are core. And then the outer shell electrons are valence. The outer shell. But we're going to redefine this a little bit. The outer shell electrons, we're going to redefine it as, the valence electrons are going to be defined as the electrons in the highest n orbitals. And so if we look at argon, well, the electrons in the highest n is 3, so these are the valence electrons, and it's full set of valence electrons. In other words, it has what we call the noble gas electron configuration, that is argon. Okay. The argon. All right, let's continue here. If we continue filling this, we'll go to potassium. Potassium has one 4s electron called 4s1. And then, actually, take a look. After potassium comes calcium, right? The 4s2. And then we go to scandium. Scandium is going to have another electron. That next electron doesn't go into the 4p. The next electron goes into the 3d. And so you can see it here on the periodic table. The periodic table is arranged in shells again. The first shell, second shell, third shell, fourth shell. The fourth shell consists of the 4s orbitals, which are the first two, and then the 3d, which is this long block, the transition metals, and then the 4p out here. And that completes the shell. Some shells will have the 4f included in there, but there wasn't enough room. So if we go to this shell, let's see, this is the first, second, third, fourth, fifth, sixth shell. When we get to the sixth shell, do you see the double asterisk here? That means insert the f in there. And so in this, we're going to see the 4f's. The 4f's actually end up in the sixth shell, not the fourth shell. They're not very penetrating. They're going to be much higher in energy. And so we insert those here, and that would complete the shell. The shell would be these S, these F's, the 6S, the 4F, the 3, 4, 5D, and then the 6P. That would be the entire shell. And so here, we're at scandium, and then we go on to titanium, and then vanadium, and then chromium. Oops, did I make a mistake? I guess I made a mistake this morning. It's not manganese. going to fix it, unfortunately. It turns out there's stability. Of filled and half-filled shells and subshells. When I have a filled shell, it's stable. It's got that spherical symmetry. But even if it's not a filled shell, if it's a filled subshell as well, like if I'm just looking at the p orbitals all combined will give us that spherical symmetry as well. And the same thing with the d orbitals. The d orbitals will give us that symmetry as well. And so there's a major exception that you have to know for chromium. When we do chromium, we expect this. We expect to have, this is called an electron configuration. Electron configuration is an even more compact representation. But it also gives us the least amount of information. And so what were the differences? This is called a energy level diagram. When I had the boxes out here, the boxes are called an orbital box diagram. And the most compact way of representing it is by doing electron configurations. And so if we do electron configurations, chromium is like this. Chromium has the argon core, we say, and then 2 electrons in the 4s, and then 4 electrons in the 3d. 1, 2, 3, 4, right. And so what does that mean? Well, that means it's going to look something like this, where 4s, we got 2, and then we got the 4 p's. The 4 p's are actually empty here. And the next higher energy orbitals will be the 3ds. We're 1 electron short of a half-filled 3D. And a half-filled 3D, what's the advantage of having a half-filled 3D? A half-filled 3D has spherical symmetry. And so if we promote this electron up to here, then this is what we're going to end up with. We're going to end up with just 1 electron in the 4s. Still, the 4p are going to be empty. But the 3d are going to have 5 electrons in. And so, 5 electrons versus 4 electrons, what's the difference? The difference is this. Let's say you had a cake, and you ate half the cake. If you ate like half the cake like this, then you don't retain that symmetry here. But let's say you cut the cake not like this, but you cut the cake like this, right down the middle, around here. Then you're going to have half the cake and then retain that symmetry. And so something like this is half the cake, something like this is half the cake with a slice cut out, right? And so it doesn't have that spherical symmetry. Whereas this would just be half the cake, like this, and it retains it. So this is not the way we look at a half-filled subshell. And so we have this half-filled subshell, the 3D, which is going to get some additional stability in that. And so for chromium, 1 electron gets promoted up here, and we get that half-filled. Once we're past chromium, well, actually, chromium's electron configuration is going to look like this. So we have argon here. And so chromium is argon 4s1 3d5. Boom. Okay, then we go to manganese. Manganese is going to be 4s2 3d5. From manganese, we'll go to iron. Iron, we're going to have to pair these. So just go ahead and pair it. Cobalt, pair it again. Nickel, pair it again. And then after nickel comes copper, where we pair it again. When we get to copper, we see something again. We're 1 electron shy of half filled. Well, we got 2 electrons here, so why don't we just promote 1 electron here and fill it? Well, that's exactly what we do. But, you know, for nickel, we are 2 electrons shy of a filled D subshell. A filled D subshell would be stable as well. And we have 2 electrons here, so why don't we promote both these electrons up here and get a filled D subshell? Well, the situation is promoting 2 electrons is not going to pay off. That is, it's going to cost you energy to promote the electrons, but you don't get enough energy in return from the stability of the 3D subshell. Whereas promoting 1 electron will give you that return. And so when we get to copper, then that's 1 electron shy. If we promote this electron from the 4s up to the 3D, then we end up with a filled subshell. So it's going to look something like this. Copper is another exception here. And copper is going to be argon, 4s2, 3d9. But 3d9 is just 1 electron short. And so what is observed is not this. What's observed is argon, 4s1, 3d10. And so we have a filled subshell. Filled subshells are fairly stable, the D subshell. See. All right, so what we can do is we can use the periodic table as a guide. Since the periodic table is set up with the shells, let's go ahead and determine some more complicated electron configurations. You'll see 2 styles of periodic tables here. All right, so we have the s orbital, the p orbitals filling this block, the d orbitals filling this block, and the f orbitals filling these blocks here. F orbitals, there's 7 F orbitals, so a total of 14 electron capacity. There are 5 d orbitals, so a total of 10. There are 3 p orbitals, so a total of 6, and 1 s orbital, a total of 2. There are 2 styles of periodic tables that you'll see, and the 2 styles come up because of this. If we look at electron number 55, we're at cesium. Number 56 goes into barium. And then number 57 goes into lanthanum. But number 58 does not go to hafnium. Number 58 drops down here to cerium. And then it goes across. And so the other style of periodic table you're going to see does this. The other style of periodic table takes the lanthanum and the actinium and puts it down here. And so really, there should be 14 electrons in the F. So when we count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's enough to fill up 7 orbitals. But there's a 15th here. How can you put 15 electrons in 7 f orbitals without violating the Pauli exclusion principle? You don't, because these first two belong to the D's here. And so there are two styles. We're going to use that style right there. Not this style. The numbers are kind of hard to see here. Let me get one with bigger numbers. So let's try to figure out the electron configuration for tungsten, element number 74. Tungsten. For tungsten, well, what shell is that in? Well, that would be the subshell. It's in the D subshell. But as far as shells, the first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. Should be in the sixth shell. Here. All right, to save ourselves some time, we're not going to do the energy level diagram, because that would be a lot of orbitals to draw. What we're going to do instead is we're going to do the electron configuration for tungsten. And so what we do is the fifth shell is completely filled. The fifth shell would be equivalent to xenon. Xenon has a filled fifth shell. And so we'll use the Nobel gas electron configuration abbreviation for that. And so if I want the electron configuration for tungsten, I wouldn't start from the beginning. I would just start from xenon. Xenon with 54 electrons. Now, tungsten has 74 electrons.
So you don't use the noble gas in the same row as it? You use the preceding one?
Yeah, you have to use the preceding one because the noble gas in the same row would have a filled sixth shell, and it would be radon. But the sixth shell isn't filled. We stopped at tungsten. Here. And so noble gases, we want the filled. All right, so that takes care of 54 electrons. The 55th electron goes into 6s. The 56th goes into 6s. So we complete that. And so for tungsten, we have this. It's xenon 6s2. And we just follow the numbers. The 57th electron goes where? Well, in this shell, this is the 3D, this is the 4D, this would be 5D. So it'd be 5D with one electron. So we go over here. 5D with one electron. But the 58th electron is not hafnium. Hafnium is the 72nd electron. The 58th electron is, do you see the little arrow? Connects you down here. The cerium. The 58th electron goes to cerium. 59th, etc., all the way to the 71st electron. Lutetium. And so we fill the entire F block, and that's the 4F. So this 4F14. And then the 72nd electron, we go back up here, that's hafnium, and that's 5D. And so we get another 5D electron, tantalum's another 5D electron, and then finally tungsten. And so we need 3 more 5D electrons. And so this is the way it fills here. 6s2, 5d1, 4f14, 5d3. But you see, what we can do is we can just combine these 5ds. You know, these are all 5d electrons. And so what we'll do is this. We'll go xenon, 6s2, 5d3, 4f14. Do something like that. Alternatively, what's often done is, okay, this is the filling order, but what we could do is we could just change the ordering here to numerical order. And so it'd be 4f14, 5d3, 6s2. So we go 4, 5, 6.
So if you combine 5d1 and 5d3, what is still 5d3?
No, 5d4. Sorry.
And at the top two.
Yeah, this should be 5d4. Mistake. So, why do we write it like this? We write it like this is because how we define valence electron. Valence electrons are the electrons in the highest n orbit. And why do we call them valence electrons? Well, valence electrons should be the outermost electron. The outermost electron, you look at this chart, and it looks like the outermost electrons are, in this chart, will be the Ds. But are the Ds really the outermost electrons here? Well, the Ds are going to be the highest energy electrons here, but are they the outermost electrons? Well, they aren't going to be the outermost electron. Actually, I didn't see the figure I was looking for, but basically this. If it were the hydrogen atom, then we know about the Bohr radius. And so, for example, if n is equal to 3, it's in the third Bohr orbit. The third Bohr orbit has a radius of n squared a naught. And so it'd be 9 times a naught. And then the fourth orbit, n equals 4, would be 16 times a naught. And so, you know, n equals 3 is 9 times the distance out. N equals 4 is 16 times the distance out. And so this orbit, the n equals 4, the 4s orbit, is going to be on average much further out from the nucleus than the n equals 3 orbit. Okay? The reason why the 4s orbit is lower in energy is because the 4s is a more penetrating orbital. And so probably the easiest way to see that is not from the wave function that we're going to show, but from another function. Which has to do with this thing. This is a 1s orbital here. And so if we're looking at a 1s orbital, we see the nucleus is in the center here. And then we see a whole bunch of dots. Those dots are just mapping out psi squared. You know, psi squared, when we look at psi squared, right at the nucleus seems to be the greatest density of dots. The greatest density of dots is going to give us the highest probability. And so when we're looking at this, the dot diagram, or the electron cloud, what we see is this. You know, the highest probability next to the nucleus, and the dots thin out as we get further and further from the nucleus. And so in a 1s orbital, where's the most probable distance for finding the electron? You know, where's the highest probability? The highest probability is right at the nucleus. And so right at the nucleus, is that the most probable place you'll find an electron? It turns out it isn't. It isn't. You know, if we're thinking about the most probable distance, we have to think this is a spherical cloud, and what we're thinking is, okay, if we're this far away, you know, what is the probability of finding? So what we do is we divide this into little rings, like onion. Excuse me, like an onion skin here. We have different layers, and each layer is going to have the same thickness. And so when we look at the first layer here versus the second layer, you know, is it more probable to find an electron in the first layer or the second layer? It's going to be the second layer. And do you know why? The reason why is even though the density of dots is less, the second layer has just much greater volume. And so when you count the actual number of dots, the second layer is going to have way more dots than the first layer. And so what we're looking at is something like this, where we're looking at the probability and then we're looking at the volume. And so if we're interested in the most probable distance, then that distance is going to be either in the first, or the second, or the third. What we'll do is we'll just make little rings around this, and then we'll take a look at the volume of the rings. And the volume of the rings will increase, right, with distance. And so the rings out here are going to be huge volume, but there aren't going to be that many dots because the density of dots goes way down. And so out here, the volume's huge. This is volume for this, but the density of dots is small. So what we want to do is we want to maximize both functions. We want to maximize the probability, and we want to maximize the density of dots. When we do that, we'll see we get a curve that looks like this. Okay, at this distance, we have the greatest volume and the greatest density of dots. And so this should be the most probable distance here. That function is called an RDF or an RPD. This is a radial distribution function, or it's also called a radial probability distribution, RPD. Probability distribution. I think most people call it an RDF. And so when we plot out the RDF, it's going to look like this. It's going to tell us where the maximum number of dots are at a particular distance. And the maximum number of dots are going to be something like this. And then if we determine that distance happens to be, for the hydrogen atom, 53 picometers. And so 53 picometers is the effective distance of 1s orbital, because it's the most probable distance of finding that electron. 53 picometers. Picometers is about a half an angstrom. So 1s orbital is about half an angstrom here, is the most probable distance. Although we can't pinpoint it here, it's not always going to be here, sometimes it's going to be elsewhere. But this is the RDF. When we go to a 2s orbital, you know, 2s orbital, higher energy, and if you look at the effective distance of a 2s orbital, it's around 6 angstroms here. A 2p orbital is around 4 angstroms here. But you know, the funny thing was, yesterday I said the 2s and the 2p have the same effective distance, therefore they're the same energy in a hydrogen atom, right? But when you look at it here, it looks like the 2s is further away and the 2p is closer. If the 2p is closer to the nucleus, then it should be lower in energy. But what we have to do is we have to normalize it over 3 dimensions, because the 2s is spherically symmetric. And therefore, 6 angstroms would be over the whole 3-dimensional sphere. So you imagine the electron being 6 angstroms away in a 3-dimensional sphere. Whereas in a 2p, it's localized. That is, you have these 2 lobes here on the px. And there's no electron up here, there's no electron down here. So to gain, to get the exact same electrical interaction, it has to be a little closer, right? Because there's no interaction above and below and in front and behind. It's only on the left and only on the right if I'm looking at the x. And so both of these normalized over 3-dimensional space have the same effective distance, which is around 6. And so these would be about 6 angstroms out. When we go to the 3 effective distance is going to be around here. You know. 3Ds look a lot closer, but you got to spread it out over 3D space again. When we go to the 4, n equals 4, the n equals 4 are going to be even further out, right? The n equals 3 is around 12, let's say, 13 angstroms. N equals 4 is going to be out. And so if this were about 12, or let's say 9 here to the 3D at 9 angstroms, the 4s is going to be at, well, if this is 9, 3 squared is 9, the 4s should be about 16. And so the 4s is going to be out here. This is a very crude calculation, but just to give you an idea. But the 4s happen to be more penetrating, and that's why they're lower in energy. But the 4s are going to be further out. And so the 1s are the closest, so the n equals 1, n equals 2, the next closest, n equals 3, and the n equals 4 are going to be further. And so this is why we define the valence electrons like this, and this is why sometimes we'll rewrite this. And so when we look at tungsten, what we see is we see 2 valence electrons here. The outermost electrons will be the 6s. It didn't fill that way. The 6s filled first, and then the 5d, and then the 4f, and then the 5d again. This is how it filled. But if an oxidizer were going to come here, and let's say you're an oxidizer, the oxidizer is not going to attack an inner electron, because the first electron it should encounter is not a 3D. The first electron it's going to encounter would be a outer electron. So here, if an oxidizer comes along, actually let's ignore this because this is more complicated. If an oxidizer comes along, will it pluck a 3D electron or will it pluck a 4s electron? So an oxidizer comes along, what's the first electron it's going to see? A 4s. And then a 3D. And so it's confusing. It's confusing because you would think a 3D would get plucked off first. It's higher in energy. But the 3D doesn't. The reason why it's higher in energy is because the 4s is more penetrating. And so we could see that here. When we compare the orbitals, s orbitals are more penetrating than the others. So for example, if we look at the 3s, a 3s has this much probability that it's going to be this close to the nucleus. If we compare that to a 3p has this much probability. And when we compare it to a 3D has that much probability, pretty much baseline, nothing. And so as far as the penetrating ability, the 3s are going to be much more penetrating. As far as this goes, well, 3D compared to 4s, a 4s, even though it's going to show the biggest hump out here, that is the most probable distance is going to be out here, it's going to be more penetrating because there's going to be a small lobe in here. All right. And so filling these, we fill the 4s before the 3D. In reacting these, we do the opposite. And so what we often do here with these electron configurations is rearrange it. Once we figure out how they fill and fill it like this, then we'll rearrange it into alphabetical order. The reason we rearrange it, not alphabetical, sorry, numerical order. The reason we rearrange it in numerical order is because this is the order of attack that it's going to be attacked. Oxidizer comes in here, it's going to take these electrons first. And then these. No, it's always going to hit the outermost electrons. And then these, if you can. And it depends on how powerful the oxidizer is. And so we'll rewrite it. Uh-huh.
How does it happen that the 5D one is filled first? Like I see it there, but from the little chart, you know, that looks like going down with arrows. It says to fill first the 4F and then 5D, but then no one gets.
Yeah, when you get to higher and higher energies, the orbitals get closer and closer together. And so for the heavier elements, there are a lot more exceptions because an electron might pop into this orbital, there's very little energy difference between those. And so how does it happen? Well, it just so happens that that's what's observed, you know, and so it must be not much energy difference between the 4F and the 5D for the first one, and then the second one goes into the 4F. A lot of people just skip that, but there are more exceptions there, and some of the exceptions are shown on the periodic table like this, and others aren't.
Okay. We won't get marked off if we follow this.
No, you follow the periodic chart, and you'll be fine. The only one that you have to really memorize is for chromium and copper. Right. All right. All right. Let's take a break, and then we'll just finish this up.